Okay, welcome back. So now we're going to start by giving some definitions of games, some basic definitions of how we represent games, players, strategies, and payoffs. And what we'll start with is what's known as a normal form representation of a game, also known as strategic form, and it's the simplest representation of a game. And in particular, what we'll do is first we'll go through these basic definitions of how games are represented, and then we'll talk about how to solve them. So in terms of representing a game, there's basically three main ingredients here. So we have players, strategies, and payoffs. And let's take those each in turn. And in particular, we'll start with players. So in terms of the players who we'll include in a game are the people who are actively making the decisions in the game. And it's not always an easy, completely cut and dry problem as to how one models a situation. So for instance, if we were thinking about modeling countries negotiating, so say the United States is negotiating with another country, do we represent those as countries, each as one player? So the US is a single player maximizing some particular payoff? Or is the United States actually a group of politicians who might have their own agendas? Or is a country a population of people who interact in a very complicated way to make decisions? Depending on how detailed you want the model to be, you might represent the players very differently. So there's a lot embedded in who we think the players are in the game, and generally we'll start with some set of players as an accepted starting point. And then we have to decide what are their strategies. So what are the possible actions that each player can take? Is passive and active enough of a distinction in order to really capture the details of what's going on in a predator-prey relationship? Well, probably not in full detail, but at least in terms of getting a broad cut at things, it might be. So how we choose to model the strategies and the actions that are available to different players will make a difference in the type of analysis and the richness of the analysis that we end up with. So when we get to a normal form, we have then a set of players, and we'll let n, capital N, denote the set. Usually we're dealing with a finite set of players, so say 1 through some little number n, so we're using little n to denote the number of players who are in the game. And then each set of players has some set of actions available. So are they active or passive in the predator-prey relationships? We'll look at different sets of actions and different examples. So we'll have some set A sub I where the subscript I indicates the player to whom that action set is attached. So these are the actions of player I. And it could be that different players have different types of strategies. So it could be that predators have different strategies available to themselves than prey. Profiles of actions are then going to be n tuples of strategies or actions. So in particular, when we have the cross product of the different actions, we'll let A denote the full set of actions. So an element A in A would then be a specification of A equals what is person 1 doing, player 1, what is player 2 doing, all the way through what player n is doing. So it's going to be an n tuple listing what every player does in the game. And then in order to be able to say something intelligent about how players are going to act, generally the way that this is modeled in game theory is to assume that there's some sort of payoff function or utility function. So utility function is going to tell each player, player I for instance, as a function of the actions taken, what's a number which represents how well they did, what's their payoff. So this will also be referred to as the payoff function. And it tells us how each player evaluates each set of actions in the game. So just in terms of examples, if we go back to our predator-prey relationship, we represented that as here n was the set of 2 players, the predator and the prey. They each had action spaces, in this case, that were identical. They could either be active or passive, so they each had 2 actions available. And then we represented these in terms of payoffs by a number which represented how well they each did as a function of this pair of actions that were played. So if they both were active, then the predator got a payoff of 2. So here the predator is listed as the row player. So player 1 is often listed as the row player. Player 2 often be listed as the column player. So we have 1 over here, the predator, 2 over here, the column player, and then the entries in the normal form then indicate what the payoffs are. So the row player's payoff generally comes first. So if they're playing active and active, then the predator, who's player 1, the row player, is getting a payoff of 2. So each cell lists the 2 players' payoffs as a function of what the actions are. So if they're passive and active, then the predator is going to get a payoff of 3, and the prey will get a payoff of -6, and so forth. Okay, so this is what's known as the normal form representation of a game, or a game in strategic form. Here's another example, a simple collective action game. So think of 2 players. They can both decide whether to revolt against an authority or not to revolt. If they both revolt, then they're successful. So player 1 here can choose either revolt or not. Player 2, the column player, can choose to revolt or not. If they both end up revolting, then player 1 gets a 1, player 2 gets a 1. They're successful in their revolution. If only one shows up to the revolution, that's not good for the person who shows up. They're not strong enough alone to have a successful revolt. So for instance, if the column player revolts and the row player chooses not to, well, the row player stays home, gets a payoff of 0, regardless of what happens then. But the player who goes to the revolution, the column player in that case, gets a -1. So this is a game where if they both choose to revolt, they get a payoff of 1. If they both don't, nothing happens. They get a payoff of 0. If one revolts and the other doesn't, then the one who revolts is in a failed revolt and actually does worse than not revolting in that situation. Okay, so this is a collective action game. They'd both like to get the higher payoff from the revolution, but they don't want to be there unless they're sure the other person's going to revolt. So in terms of the players and the action spaces and the payoff function here, the set N is the set 1, 2. The actions are revolt or not for both players, so this is a symmetric game. They both have the same strategy space. They both have the same payoff function as a function of the possible pairs of actions for themselves and for the other. In this case, if they both revolt, they get a payoff of 1, and so forth. So we can represent that in terms of listing the N, the AIs, and the UIs, or often if it's just a 2-player game, it'll be represented simply in terms of a matrix, which lists the actions for the row player, player 1, column player, player 2, and then in each entry lists what each player gets as a function of those possible actions. Okay, so let's make a few comments just about payoff functions or utility functions in a game. It's very important to specify them because they're going to determine what the players want to do and how we solve games and what predictions we make. And if you get the wrong payoff specified, you'll get the wrong kinds of predictions. And in particular, one thing that's very important is understanding what motivates players. So is it just simply their own payoff, so they're completely selfish and they care only about what their payoff is? Are they altruistic? Do they actually care about what happens to other players in the game? So if we're in a situation where there might be relationships between the players, there's friendships or families or other situations where one person cares about another, they might care about how the outcome affects the other person in evaluating what the payoff should be for a particular set of actions. Do they care about relative outcomes? Is it a situation where they want to be better than somebody else? Do they care about fairness? Do they care that they get as much as somebody else does in the game, or they're as successful as somebody else? So all of these kinds of things can enter into people's considerations in terms of how they evaluate actions. And to the extent that these things do, we want to make sure that we've represented those properly in the payoff function, and that the payoff function is capturing exactly what is motivating the players in terms of choosing their actions. Okay, let's talk quickly about two interesting families of games, ones that have been fairly well studied. Team games, or the essentially fully cooperative games, in the sense that players will get the same payoffs as a function of the actions and would like to coordinate. And then the antithesis of that, zero-sum games, where players are really in competition and one player's gain is another player's loss. So a simple example of a team game is just a pure coordination game. Here players can choose either left or right, for instance, which side of the street they drive on or which side of the sidewalk they walk on. If each person going in a different direction chooses to always go to their left, that's fine. They avoid each other. They'll get each a payoff of 1-1. If each player goes to the right, they avoid colliding with each other. So each person goes to their own right, then they avoid each other. But if one player is following a convention where they go to the right, the other person goes to the left, then they hit each other. They're not getting as high a payoff. So they get 0 payoffs when they collide, and otherwise are doing well. So this is an example of a team game where the payoffs to the players are basically the same for both players as a function of whatever happens in terms of the outcomes. For any two players, then, in terms of a team game, and we look at an action profile A. So this is a profile, for instance, A1 through AN when we think of a team game. Then when we look at any two players, no matter who they are, as a function of A, they're getting exactly the same payoff. So they share exactly the same incentives as a function of the actions. A more general condition is that people have identical preferences over strategy profiles. We'll talk about that a little later in terms of strategy profiles when we talk about mixed strategies and so forth. But effectively, the definition extends directly when one allows for mixtures and other kinds of more richer games in terms of timing. And effectively, these are also known as pure coordination games, common payoff games, team games. They'll go by a variety of names, but these are games where there's a strong coordination in the player's interest, or congruence in the player's interest. Okay, another class of games, zero-sum games, are ones where players are in pure competition. Here are two of the most basic examples of zero-sum games. So zero-sum is the situation where the sum of the payoffs to the two players is always equal to 0. And here, for instance, matching pennies, this is a situation where players are choosing either heads or tails. The row player is choosing heads or tails, column player is choosing heads or tails. Row player wins if there's a match in the two players' actions. So either both heads or both tails. But the column player wins if there's a mismatch. So the column player would like them to mismatch, the row player wants to match. Matching pennies, simple game. The game that you saw Yoav and I playing on our introductory video, rock, paper, scissors. That's a game where each player is choosing rock, paper, or scissors. If they both choose the same action, there's a stalemate, nobody wins. If the row player, for instance, picks paper, and the column player chooses rock, then the row player wins. 1 minus 1 is the payoff, etc. So rock, paper, scissors is a simple game. You can represent it here. Again, it's a game where one player wins, the other player loses. So there's a positive payoff for one player, a negative one for the other, and they balance out and sum to 0. Rock, paper, scissors, also known as Rochambeau, a very simple and classical game. So zero-sum games generally The interesting cases will be limited to two-person games. So often when we refer to zero-sum games, we're referring to two-person games. You can have a general n-person situation where you've got a zero-sum game. But the idea here is, again, that the payoffs of the players as a function of the actions sum up to 0. There's a classic result by von Neumann and Morgenstern in the 1940s that said that basically any n-person game can always be converted into an equivalent n+1 person zero-sum game. You just, whatever's left over that doesn't sum to 0, you have the n+1 person's payoff be equal to the minus of what the sum of everybody else's payoffs are. It always sums to 0. And in some sense, that's been interpreted as saying that that the interesting situation is when you're dealing with zero-sum games. And we'll see that some of the results, the classic results in two-person games and zero-sum games are really somewhat special to two-person games. Very important point, 0 is not critical. Everything you can say about zero-sum games, you can say about constant-sum games. So it's not important that they sum to 0. They could sum to some number k, for instance, as long as whatever benefits one player, if they get a payoff above k, then the other person has to be pushed down below k. These are also known as games of pure conflict, pure competition. They're adversarial games. And a lot of the early work in game theory was on two-person zero-sum games, partly because they have a nice mathematical structure. And a lot of the early work was done by mathematicians in this area. And there was a number of interesting theorems that they proved in that time.